All right. Good afternoon, everyone. So my name is Leandro. I'm going to be delivering this presentation on behalf of my PhD student, Anna Bergmann, that couldn't make it. And this is going to be about a topic related to internal solid reactions, more particularly to alkali-aggregate reaction in concrete. So everybody knows in Canada and worldwide, I would say, alkali-aggregate reaction, which can be divided in alkali-silica reaction and alkali-aggregate reaction, is perhaps amongst the most harmful deterioration mechanisms affecting concrete infrastructure. We can see a wide range of structural types affected by AAR worldwide: bridges, dams, tunnels, stadiums, and so on and so forth. The community has been dealing with such an issue for many, many decades. The rehabilitation processes and evaluation processes improved a lot over time, although I think it's quite, by the way, we have AAR everywhere in Canada, including in our own campus. So this is our site building, only 15-year-ish, perhaps 20-year-ish structure, presenting signs of alkali-silica reaction with some gel and some cracks and deterioration of the aggregates. So after all of those years studying alkali-aggregate reaction, it's a consensus in the community that the best solution is to prevent this problem. So whenever we have ASR, or alkali-aggregate reaction, AAR, in affected infrastructure, it's quite difficult to rehabilitate it, if possible. So we can perhaps try to mitigate the problem, but really solve the issue is very complicated. In regards to test procedures that we can have, and they're pretty much standardized worldwide for assessing the potential reactivity of aggregates and combination of aggregates and binders regarding AAR, we have two that are widely spread, which is the Accelerated Mortar Bar Test and the Concrete Prism Test. The Accelerated Mortar Bar Test, for those that don't know it, we fabricate a couple of bars, little bars, and we soak that. We crush the aggregates to reduce down to the grading of sand, and we soak the bars in an environment that is very aggressive, 1 molar sodium hydroxide with 80 degrees Celsius for 14 days, if not 28 days, normally 14 days, whereas the Concrete Prism Test is a test in which we test the coarse aggregate in its coarse fraction, or the sand aggregate in its sand fraction, and we cast 75 by 75 by 285 millimeters prisms, and we store that into conditions enabling ASR, normally 100% relative humidity and 38 degrees Celsius, and we allow swelling for 1 year. So this test is largely used worldwide in practice because it's quite cheap and quite quick. Otherwise, in research, we believe that is not really accurate, and because of that, we always try to talk to the community so that we do more longer-term tests, because normally they tend to be, at least without any type of quantification, but based on expertise and based on experience, a little bit better. But we know that both of them are, although it takes a year, it's still called accelerated, because alkali-aggregate reaction in the field may take 10 to 15 years. So trying to understand what's going on under real exposure, several people in the world, they constructed exposure sites in which they expose blocks or slabs or beams, different types of structures, reinforced or no reinforced, and they measure expansion, deterioration over time. There has been several exposure sites built in North America, Europe, Asia, and so on, and including one in Ottawa that has been constructed by my former supervisor, Ben Fournier, in the early 90s, and it reached 30 years old of measurements and so on. It's very interesting. And from those days, people from the community keep publishing about the use of those accelerated tools to forecast performance of AAR. And testing procedures have been a huge debate in the community. So in the past ICAR, that was in last year in June, in May actually, we in Ottawa, 70% of all of the 60 to 70% of all of the papers received were on testing, and they were disagreeing to one another. So you can see, for instance, in 1999, a paper saying that Accelerated Mortar Bar Test and the Concrete Prism Test, they both did a good job. But then in 2016, the Concrete Prism Test did a good job until a 10-year exposure, but after that, it started lacking a little bit of precision. Going on another project in 2008 saying that both tests are kind of inconsistent, whereas in 2010, they said that they were kind of successful to detect aggregates, but not necessarily all of the sorts of aggregates. So there is a gap in here, definitely. What is the gap? The gap is that our tests, we know by experience and not trying to put any numbers out of it. If you talk to labs, if you talk to engineers involved on AR, we are not sure that what we measure in the lab represents field. And what I tried to do with Anna in her PhD was try to put some numbers on those values, on those data that we gathered or data that have been gathered before. So, are the current used versions of Accelerated Mortar Bar Test and Concrete Prism Test reliable or not? And how these test outcomes could be better used to assess and quantify risks associated to AR? Because every time a test doesn't work, we want to change the test. And one of the challenges we face a lot trying to put that work together is that there were lots of data from different tests that we could not compare to one another. So isn't better, instead of trying to develop a new test, then labs will not be able to do that because they do not have the formworks, they do not have this or that, to use better the test outcomes, to understand and do an engineering judgment on the test and use it via a model or something. So that was the idea. And then Anna developed a great PhD that she finished a couple of months ago. And we divided that in 3 phases, and we split that into 5 papers. And I will try to kind of give a brief of results for you in this presentation. So first, what we need to do was quite cool. We need to try to find data. And since this project has been also in partnership with a RILEM group in Europe, led by now Jason Neidecker, that probably most of you know, we were intending to get data from colleagues from Europe and North America, but believe it or not, nobody wants to provide data as long as it's not published. So there has been a huge problem to try to find some data and put the database together, but we were able, and I did an immense amount of work to try to grab all of the data available, published over the last decades, and put together a bibliometric analysis to see which were the countries that we need to approach those guys to get further amount of data to develop our database. So that was the first thing. Second thing, we used very conventional statistics just to assess in a kind of semi-quantitative manner the results. Then we tried to play a little bit with better tools, adopting some probabilistic modeling, using some decision trees and some AI-driven methodology. And finally, we try to provide a framework of a better use of results associated to tests. So let's try to summarize what has been done in each of those papers. So the first paper, we decided to do a bibliometric analysis to see which were the works that were performed worldwide, in which we could have what? Accelerated tests, and from the same mixes, data from exposure sites, because not having exposure sites, we wouldn't have a control, and we were not able to compare whether those results were reliable, right? And it's very interesting that we notice quite clear that Canada and US have been largely the countries working with Alkali-aggregate reaction. And, Kevin Folliard, Ben Fournier, Mike Thomas, Marc Andre, all of those guys have been producing lots of data from the lab and to the field that could be used. So we had an idea that we needed to approach those guys to get data, approach papers from those guys, but that bibliometric analysis gave us the right road to go against and get some data. So, what is the reliability of the test methods? Is that dependent on the field environment? to try to answer that, and knowing that Canada and US would have been the ones with the largest amount of data for us, we decided to select two exposure sites to start with. One in Ottawa, which is a cold environment, versus one in Texas, in Austin, with, we call that a warm environment. So we would like to see mixes with the same aggregates, same cement, same everything, just the influence of the environment on those guys. So then what we have done, we did simply a very simple statistic. So we plot all of those points. Each of those points were correlations between field and, for instance, here, the Accelerated Mortar Bar Test. Field is whenever it reaches a given expansion over time. At the last expansion, some of the results were measured at 25 years, some of the results were measured at 30 years. And the Accelerated Mortar Bar Test as per ASTM, for instance, 1260. And you see that whenever you are here or there, you are okay. Why? Because you are measuring the same thing, meaning that here, your test tells you, well, I don't have an aggregate that is reactive, and you don't have cracks in the field. And here you have cracks in the field, and you have an aggregate that is reactive. But you can see a large amount of aggregates that are in the red zones, meaning that we have a misclassification between lab and field. And then we have opened up that for mixes without SCMs and mixes with SCMs, knowing that for ourselves in the world and research of alkali-aggregate reaction, whenever we have mixes without SCMs, our intent is to test the reactivity of the aggregates. Whereas whenever we have with SCMs, our intent is to see the performance of that mix, aiming to mitigate the potential reactivity of the aggregate. And you look at those and you see, well, I will have lots of issues in the field, because if you look, some of them are well classified, but most of them are not well classified. Now, in order to try to understand how bad we are and how far we are on the reality, we have done a simple statistical analysis in which we try to get how accurate they are. So we evaluated that where, for instance, this is not accurate and not precise. It's very precise whenever they are close to one another but not accurate. Accuracy is whenever you are right at the target and they are close to one another. So we try to come up with those basic numbers to understand, and then open up for the mixes without SCMs and with SCMs. We see that the performance of both of the tests are not great. 25% of everything we test, we get it wrong. So, and it should be noticed that for those aggregates that were used in this research are normally the aggregates that, for those that work in the AAR community, we call the aggregates that behave well. What does that mean? It means that our aggregates with very known behavior, we know what they should get in the accelerated test and so on, meaning that this, based on experience, if we could get aggregates that are tested elsewhere, could have been half of it. When we use SCMs, the precision, it's 50%, so you flip a coin, right? So we are really, really far of having a good test method, and we knew that. It's very interesting because when my student was able to put that together, people said, well, but we are doing bad, but we know that. We've been discussing that over the last 3 ICARs. ICAR is every 4 years. So we know that. The problem is that we do not do anything to try to counteract that. That's the problem. Now, what we try to do, and Anna started doing lots of statistics studies and so on, and we collaborate with people in the field. We said, well, why don't we try to get that in a more probabilistic fashion, and we try to use Bayesian statistics in which we got our prior probability, so knowing the amount of reactive aggregates over the total amount of aggregates, the likelihood function, which is a function that lets us know what is the likelihood of reactivity based on the different variables we are evaluating, the marginal likelihood, which is a summation on all of that together, giving an overall perspective, and computing these three, we are going to be able to compute our posterior probability. And we decided to plot all of that in what we call a beta distribution, and we try to compute a Breer score, which will be the score of how well the computations were, ideally close to 0, if they were very well computed, and badly computed close to 1. So basically, we were able to put together that plots in which we could split in non-reactive cases, meaning that I know my aggregate is not reactive, and reactive cases. So ideally, my green curves would be close to 0, my blue curves will be close to 1, and so the average would be, as I mentioned, 0 and 1. And if we open up to all of the mixes I showed you before, we see that, for instance, for mixes without SCMs, the Concrete Prism Test, I have about 70% accuracy. And again, for the Accelerated Mortar Bar Test, I have about 70% accuracy-ish, okay? And regarding non-reactive aggregates, both of them, sometimes they give the so-called false positives. And the CPT, the Concrete Prism Test, gives even more false positives. So basically, we are having very likely false negatives and also false positives for both of the tests. Well, that's not good. With SCMs, the same thing, but SCMs, you see, whenever the aggregate is reactive and you can come up with a reactivity using that, is 50%. Again, you are flipping a coin, right? So we have a problem. And besides getting to AI and so on, what I told Anna is that an engineer, normally, whenever there is a test, to use that aggregate or that combination of aggregate and cement is based on a threshold of a test, which is bad, as it has been seen here. Why not trying to create a type of a risk? What does that mean? It means that, well, what's your risk of using that aggregate if it has been classified as reactive, for instance, in above and beyond 80% of the cases? And then we will consider that very low. Whereas, for instance, if your risk is high, if this aggregate has been considered less than 60% of the cases. For instance, we created that, and then we adapted that for our mixtures with and without SCMs, and for cold and warm environments, because depending if it's cold or warm, the risk associated with using a single value of a same test could be different, because the field performance is going to be different, right? So for instance, if an aggregate is non-reactive, if you use it in a warm environment, perhaps it's going to react, and this is what we are seeing in Texas, and then there is a high risk associated with using the test to make decisions. Otherwise, in a cold environment, normally they're going to match lab and field, so the risk associated of using that is not a problem. Same thing for reactive aggregates, in which actually the upside down. For reactive aggregates in a cold environment, perhaps is not going to react that much. For instance, the same amount of expansion the Accelerated Mortar Bar Test for Ottawa is fine, but for Austin is not. And then we are going to have risk associated to that. So we put together not trying to solve any issue, but at least to provide an engineer with a supplementary tool to make decisions, right? So I'm not only using that data anymore, but I'm saying, so I'm accepting that, but what is the risk associated with that acceptance? Then we try to, in paper number 4, we try to help engineers to make better decisions, and for this we have used decision tree processes followed by logistic regression, and the idea was try to have something dynamic, because we figured out that everything influences on everything. So how can we come up with something that could point out directions of better decisions? And then we created this type of tables for the Accelerated Mortar Bar Test and for the Concrete Prism Test that vary as a function of the amount of alkalis you have in the system. So we know that the higher the amount of alkalis, the higher the likelihood of having alkali-aggregate reaction. However, depending on the temperature and depending on the test you do, the risk associated with that value of the test is different. So basically, what you get is that what is the threshold of your test that you need to use, and what is the duration that you need to have to get a probability, a low probability, so you become green here. If you are red, you have an issue, right? So it's a dynamic evaluation because unfortunately or fortunately, everything impacts everything in that behavior. We put together those plots, so you can see that, for instance, you can go with an expansion level of, let's say, 0.2, and with duration of the test and 14, you are still okay in a cold environment for the test. But you use that same test and the same amount of time, you're going to see that your probability is much higher of developing ASR. So this gives a better usage of the outcomes instead of simply following SCM or CSCA without any further thoughts on it, and then see a huge discrepancy between lab and field. And then to finalize, what we tried to do was to propose a framework, not to give only those plots, but to try to get some hints to the community on how to use that. And this is, we are partnering with RILEM. So basically, we are developing a very structured framework. So we establish the risk of the structure that we are going to use that concrete. We gather critical input data. We compute the probabilities, as we mentioned here, and that input data could be the tests I just mentioned here. Then we compare calculated risk with acceptance limits that the client will have or the engineering charge will have. We may adjust the parameters if needed, and we're going to make an informed decision. So basically, how we could get started with that, so assuming levels of risks for different structures. So some ASR can be tolerated, very minor ASR, or moderate ASR, or very important ASR. There is no problem, nobody cares, it's going to be demolished in 10 years from now, or is a dam that's going to be there for 200 years, and then we need to take care of it. So what is the probability of that? And then what we have done is that we, on top of the dynamic tables that we proposed before, we propose routes for engineers to say, look, you want to be moderate risk for that type of the structure, so play green here. Play yellow here. If you can be in right risk and you don't care because that structure is not really important, you can play red here. If you need to be really safe regarding ASR, which is the case for the critical infrastructure, for instance, you need to be green. So you may adapt the expansion level of the test based on that. So what are the main outcomes of that PhD research? Is I think the project of Anna didn't show anything new in the sense that we know that the tests are not good. I think it's not true. For those working with ASR, we know the tests are actually very bad for many, many decades. So we knew that. What we actually didn't know is how bad they were, and they look like very bad number-wise, and they could be even worse, again, if I was using aggregates that, in quotes, do not behave well. I only used aggregates that are very well calibrated, everybody knew their performance and so on. Whenever we change mineralogy and we start using aggregates that are the so-called slowly reactive aggregates, granites, for instance, and so on, things might be way worse than this. So we are going to pretty much be flipping coins and doing accelerated flipped coins, perhaps, is the method. So Bayesian theorem can provide interesting classification, including with decision trees. I believe that if we keep changing tests, we are not going to be able to solve problems, but if perhaps we learn how to proper use the test outcomes, like we do for structures, for instance, we get the compressive strength, we input into models, and we are fine with that. I think this is the way to go, maybe for an AR perspective. Thanks for your time, and if you have any questions, I will take those. Thank you.